Welcome everyone to the fourth webinar of CompBioMed, Introduction to Biomedical Applications on High Performance Computers. CompBioMed is the Center of Excellence in Computational Biomedicine. My name is Britt van Rooij. I'm a PhD student at the University of Amsterdam and a PhD committee member of the VPH Institute, who helps organizing this webinars. I would like to introduce our speakers of today. Gavin Pringle and Gabor Zavodsky. Gavin is our first speaker. He has a background in computational fluid dynamics, and he's currently working at the University of Edinburgh, where he's working on high performance computing. And he's involved in the CompBioMed project as a work package leader for innovation and sustainability. Our second speaker is Gabor. He has a background in physics and biofluidic as computational fluid dynamics. He's currently a postdoc at the University of Amsterdam and also involved in the CompBioMed project. Before we start the webinar, I would like to ask you to wait with your questions and keep them for the end of the webinar. There are two options. So you can type in your question in the questionnaire tab in the menu, and the other one is raising your hand. Then we can open your microphone and you can ask your question yourself to the speaker. So it's time to start. Gavin, the floor is yours.
So thank you, Britt, and welcome everybody. This is an introduction to biomedical applications on high performance computing from myself and Gabor. The talk will be split into two. I will do the first half hour where I'll discuss why high performance computing, and then introduce the anatomy of regular computers, followed by the anatomy of a high performance computer, so we could compare the two. Some practical details, so how to log in, what does a command line, how do you edit files remotely, and how do you access the compute. And finally, measuring performance, or in other words, I've got access to a machine, just how many cores should I run my simulation on? Then after my talk, Gabor will take over and we'll introduce a specific HPC code called HemoCell, and we're going to be running on a particular HPC machine. This is a machine called Lisa, which is at Surf Sarah in Amsterdam. We'll also talk about how to set up your environment to develop your application on, how to run a simulation, and finally, for this particular case, how to look at the output it generates. So, why high-performance computing? So, scientific simulation and modeling has really driven the need for greater and greater computing power. And single processes really can't give you this power that you need, both in terms of speed and in terms of the size and the scale of the simulation that you want to run. So really the solution is parallel computing, to break the work amongst many different items and have all these items be worked on simultaneously, so to compute something in parallel. And indeed all high performance computers are parallel computers. So what does one look like? This is the UK National Supercomputing Service called Archer. This is a Cray, but perhaps one that's slightly more beautiful to look at would be the famous Mare Nostrum in Barcelona, which is the Spanish National Service. There it is sitting inside a church. Well, okay, a former church. So traditionally, who is it that uses high-performance computers? So it's normally material scientists and solid-state physicists. These are the real users of the machine, the vast majority. Computational chemistry, biomolecular simulations, particle physics, these are all large users as well. Plus environmental modeling, so climate change, weather forecasting, that sort of thing. And indeed, many, many engineering applications, trains, planes, cars, combustion engines, mining, tsunami warning systems, that kind of thing. But we're focusing today on biomolecular simulations. Here's the output of a particular simulation of a code called GROMACS. I put these up just as examples. Here's output from another code called NAMD, which are, so another good example, and I should press this strongly is our what we call our IMAX video, which was generated for us by Barcelona Supercomputing Centre with input from all the CompBioMed core partners. And I urge you to visit this. This is now available on YouTube. Anyway, so that's the motivational part. So what does a parallel machine look like? So this, I think this is a very good slide. It's a rough conceptual model. You can consider a collection of laptops. So in this case, we have 5 laptops, and they're connected together via a network. So maybe that's a same Wi-Fi network, or maybe they're connected with Ethernet cables through a router. Or so you can consider this as a general or generic parallel machine. Each laptop is what we would call a compute node, and each compute node has its own processor, hard disk, memory, etc., and each run their own copy of an operating system, which is typically Linux for high-performance computers. Now, let's say each laptop had 4 cores, then we would regard this generic parallel machine as having 20 cores in total. The key thing here, I think, to take away is that the performance of this generic machine we see here is highly dependent on the network. The better the network, the better they can communicate, the faster they can communicate. So high-performance computing versus other types of computing. So you can consider computing on a sort of continuum, where on one hand we have a low performance, low end, so this would be maybe your mobile phone or your laptop going up to your desktop, and as it gets bigger, it'll have more cores and more memory. So this might belong to a university research group, or maybe a departmental machine, a server or a cluster. And as they get bigger, they go pan-university, and bigger again, they'll go regional, maybe national level, right up to the point of, say, continental scale. And these machines are optimized for traditional scientific applications. So there's a very strong mathematical element to it. This for number crunching, as it's called, or more technically, a floating point performance. And they have very fast networking between the nodes. On top of this, there's also software available on these machines, which are specifically for scientific or mathematical use, and these are available via libraries. So the anatomy of a regular computer, what does that look like? So you can see that the large box there, there's a floating point unit that does the number crunching or the mathematics, and that runs at a speed of 2.2 gigahertz. And then to the right, there's a memory bank, and everything that needs to be computed on is pulled from the memory into the cache. And then this large box has access to a disk. So this is for I/O, for file storage, that kind of thing. Now the performance of this, well, it's a serial computer, was one processing unit, is dependent. So what we call performance is actually the time to solution. So our gain here is to do things as quickly as possible. So we're limited here by the clock speed, or how fast the processor is, the floating point unit, or how many operations can be performed on for every clock tick, memory latency, how fast can we actually access the data from the cache, and then memory bandwidth, how much data can we get in one go from the memory, and then finally I/O storage, how fast can we read and write to a file system. And then the advent of multiple cores came along. This was maybe a few years ago back now. My mobile phone, for instance, has 2 cores. My laptop has 4. Here's a processor with 4 cores. They all share the same cache. They all access the same memory, and they all access read and write to the same disk. Now, how do these cores all access the same resources? Well, that's through what we call the operating system, or the OS. And that's responsible for orchestrating access to the hardware. What core does an application run on? How is that application, how is the memory allocated, deallocated? What file systems need to be accessed? Who has authority, etc. And running these applications are controlled through 2 concepts for operating systems. One is processes, and one is threads. So let's have a look at processes first of all. So each application is a separate process in the operating system, and they have their own memory space, and you cannot access that by other running processes. And each process is scheduled to run by the OS. So it will run on a particular core, for instance, or depending on your setup, it might migrate and move between cores depending on the load. Now, many processes run on a single or serial, but now it's multi-core processors are available. Then it's quite common now that processes can actually split and run on multiple threads, and these threads might run on different cores. So there is an idea of parallelism built into these operating systems already. But the anatomy of a high-performance computing. So I think this is a very good slide. So on the right-hand side here, the large box. We call these compute nodes, or sometimes they're called back-end nodes. And in this case, we have 16 of them. And to the left there, we have a login node, or sometimes called a front-end node. And that is how users access this large compute resource on the right-hand side, the compute nodes. So a user, or multiple users, in fact, will log into the login nodes. They'll upload and download data to and from the machine via these login nodes, and they do this via what's called an SSH terminal, or secure shell terminal. So they will upload data, and then they want to run a job using that data. So they submit jobs to the compute nodes from the login node using a job scheduling system. So they don't actually access this very large number of nodes directly. You have to do it through what we call a batch system, which is a layer on top of the job scheduling system. And then both the compute nodes and the login nodes see the same disk. So if you put an input file up onto the login node, then the compute nodes will be able to see that disk, that file at runtime. So this is a slide which I've put in grey text. I think it's important, but not important for me enough to talk about it. So this video will be available on YouTube very soon. So please pause these and read these slides at your leisure. So I'll skip this for now, but there will be other points which will be in grey text like this that I won't cover verbally, but they're available for you in this slide deck. So as I said, all high-performance computers machines are parallel in their architecture. And sometimes they're actually constructed just using commodity hardware. By that I mean you can go into a high street shop and you can buy these components from the shelf and build your own high-performance computing machine. So there are two fundamental parallel architectures. There's the shared memory system and a distributed memory system. And typically nowadays, HPC systems feature both of these architectures. But I'll describe these architectures now. So this is a shared memory architecture. In this image, we have a large bank of memory, which is accessed by these 5 processors. And each of these processors have 4 cores, and they all have their local cache. So all cores have access to the same bank of memory. They share the memory within that node. So most computers now are shared memory machines because of multi-cores. In fact, my mobile phone is a shared memory machine. It is very difficult to build shared memory systems with large core count numbers, say over 1,000 cores. They're very expensive and consume a lot of power. So we can't really extend these machines larger and larger and larger. So the idea, an opposing idea, is this distributed memory architecture. So in this example, each processor has 4 cores, they have their local memory, but then there's another node beside that, again with 4 cores per processor with its own local memory. Now these cores, the 4 cores share memory in each node, but they can't access the other node's memory directly. You have to do that over what we call the network. So each self-contained part is called a node. Almost all HPC machines are distributed memory, but some of them tend to have shared memory within a node, and they'll have at least one multi-core processor per node. But as I keep saying, I think the performance of parallel programs often depends on the interconnect, which is another word for the network between each node. And so this really is a very common architecture. So in this example, we have 2 nodes, although there are other nodes off the slide. Within the node, you have 4 processors in this example, and within each processor, you have 4 cores. Each of these 4 cores can access their own cache, and each processor has their own memory. But within this node, which has 16 cores, they all share the same memory. So each core can read and write to the same piece of memory. Now there's a second node on the right, which is a duplicate of the one on the left. That too has 16 cores, that too shares the memory. But if you want cores in one node to be able to communicate with a core in another node, then you have to go over the network. Maybe it's worthwhile saying that you don't have to have the same number of cores in every node. You can have a heterogeneous cluster that's possible. So all HPC machines fall in this class. It's distributed memory nodes where each node has multiple cores all sharing the same memory. Most applications use a message passing model so that they can communicate between cores, whether that core is inside the same node or on a distant node. And typically the model used, the language that's the library used is MPI, with a single MPI task per core. MPI stands for Message Passing Interface. Another way of programming these machines is using threaded programming, such as OpenMP or POSIX threads. But be very clear, you cannot use these threaded programming models across multiple nodes. These only work within single nodes. So the programming modeling, how to program these things, I've just mentioned particular instances. So this would be for the threaded codes, as I said, OpenMP or POSIX threads. And these threads communicate, in quotations, essentially by having access to the same memory space. So any thread can alter any bit of data, and there's no explicit communications required between the parallel tasks. So for instance, in this diagram here, thread 0 has, let's say, owns this A0, but can read and write data to A4, which belongs to thread 1. This idea of ownership or belonging is really up to the programmer and the compiler to say who is responsible for what piece of data, but you can read and write to any piece of data anywhere. Now, on the other hand, you have this idea of message passing, where each process does not have access to the other process's memory, and communication must be done explicitly. And this is done by the programmer alone, not by the operating system. So it's up to you, the programmer, to decide what data belongs to what process and how that data is passed between them. So the alternative to this is hybrid programming, where you can use process and threaded parallelism in union. This is done with MPI and OpenMP, but I won't dwell on that. So how do you actually use HPC systems in practice? So logging in to the login node is done using SSH. These SSH shells are accessed natively. They're available by default on Macs and Linux machines, but you have to install a piece of software on Windows machines. We recommend PuTTY, but other ones exist. And this is what it looks like. This is an example of an SSH terminal, where the person is logged in, and then they can see this is called a command line interface. So it's not a GUI, it's not a web portal. You actually have to type things. You have to type commands in this window. And when you're using remote HPC resources, or indeed local HPC resources, you need to edit files that exist on that resource. And to do that, you need an in-terminal editor. We recommend Emacs and Vim, but there's many, many other ones available. And here in this example, you can see what we call a batch script. This is a script where you would say, I want 32 cores, I want to run for 10 minutes, and my code is going to be called sharpen.x. So I'll talk about that more in detail. What indeed is a batch system? So this is a mechanism to submit your jobs to the compute nodes. It controls the access to the many users using the shared computing resource. It queues, schedules the system for your job, and manages the reservation of resources. So this allows you as the user just to fire and forget large, long calculations, or maybe a single large group of jobs. These are called production runs. Typically, they're not interactive. Typically, there's no GUI. In fact, I would strongly advise not to have a GUI and not to make them interactive. So you'll submit 1,000-core jobs. They may take a few hours before they run, because this will be a large system with many, many users all queuing jobs. Once the resources you've requested become available, then they start running, and might run up to a day, maybe even 2 days at most, or indeed half an hour, depending on the problem size that you're running. So why do we need a batch system? Well, it's a very large resource, but because you have so many people using it, you have to ensure that all the users get a fair chance to access the compute resources. And we also use these batch systems to track usage, so we know how much to bill people and how to manage your budget. And we also use it to mediate access to other resources, like software licenses, for instance. So the batch system has to access the reservation and execution part of the scheduling system, which I won't talk about. And in the batch system, queues themselves also have a certain configuration, which I won't talk about. So how to use these batch systems? So the first thing you have to do is to write what we call a job script. This is in essence an ASCII file, and here you'll say to the system, I want to use a particular number of cores. I don't want the job to run more than an hour, for instance. And then here come my jobs. This is the kind of job that I want to run. So the second thing you would do is then submit this job script to the batch scheduler, whatever that is, and that batch scheduler will execute your job when the number of cores and the time is available to you. And that job will run until one of three things happens. Either it finishes successfully, it crashes due to errors, or you've reached the maximum job time that you specified, an hour, I think I said earlier. And when the job finishes, you can then examine the outputs and possibly look at any error messages that you have. So this is an example batch script. This is using a batch script system called PBS. And here we have the first 5 lines are all commands to the PBS system itself. The first is to create a login shell. The second is just to name the job. Here we've selected 3 nodes, and we want to use 36 cores in each of those 3 nodes. So we're using a total of 108 cores in total. The PBS, we want to limit our job to only 1 hour. And then finally, this is some sort of account that you'll have a budget on the system, and it'll take the time that you've used from your budget. And here are the examples to D411. Then the next 3 lines are the actual lines that are executed when it's running on the back end. So here we're going to change directory to the directory we've submitted our job from, typically our working directory. In this case, we're going to load a library called FFTW, which is a very fast FFT routine library. And finally, we're going to run a job, which happens to be an MPI job. We're going to use 108 cores, and the execution name is called WeatherSim. So this is a parallel application launcher. This is the number of instances of this parallel code we want to run. This is the program name. That's the requested job duration. Changing the directory to run in it, the number of nodes, and the number of cores per node. That's the job name, and that's the Linux shell. and also the budget. So, how do you access the batch system? So let's say we've created a batch script called batchscript.txt. Then on that command line, you would say q sub space and then the name of your script file. And that submits it to the batch system. And you can monitor your status of your job at any time using the command qstat followed by -u and then your username. And that'll report things here listed at the bottom, the second table here. So if it reports Q, then it just says the job is still queuing and hasn't started yet. If it reports R, then it's running. If it reports E, then it's exiting. Some people mistake that as an error. If it says F, then the job is finished, not failed. And if the H, then that means the job is being held by the system and it's not eligible to run. So for instance, you've asked for more cores than exists in a node, or you've asked for more cores that exist on the machine. Maybe your budget is empty, maybe, So if it's an H, then you'd have to kill your job. So if you go back up to that top table, if you want to kill your job, you use this delete command, qdel, and then the job ID, which is given to you by the qsub command. So how using these HPC systems, or specifically, I've got a simulation, how many cores should I use? So measuring performance is the key way to determine how many cores you should use for any given application and a given simulation that you intend to run. And we monitor the performance using three metrics. One is the execution time, which is simply the time running for a particular problem on a particular number of cores. The speed up is calculated in terms of how fast your simulation took to run on one core divided by how long it took to run the same simulation on multiple cores. And then parallel efficiency is the speed up divided by the number of cores that you ran on. So here's a speed up graph. This is very typical. So the number of cores along the horizontal axis, the speed up on the vertical axis, and the blue line there, the straight line, is the ideal. So say you're running on 250 cores, ideally you would like that to go 250 times faster. But typically, as the number of cores increases, the speed up actually starts to decline. Now that's because as so you have a fixed problem size, and as the number of cores increases, the amount of the problem that each core has is smaller and smaller and smaller. But you still have to communicate with all the number of cores, and the number of cores gets bigger, there's more communication. And if you're if you're communicating, you're not computing. And so this is why the speed up drops down, is because the computation isn't being perfectly divided, because there's also work to communicate, and perhaps there's I/O involved, and So this is called scaling, parallel scaling, which is where how does your code increase as you increase the number of cores on this? So if people say that their application scales, what they actually mean is that a particular simulation using their application continues to have strong parallel efficiency as the number of cores is increased. So on a practical level, I've got a simulation, just how many cores should I employ? So let's say you have 500 nodes, 32 cores per node. Maybe I can use all the cores on all nodes. That means I could run 16,000 times faster. Fantastic. Of course, it depends on what kind of package you're running. If it's parallelized using threads, say POSIX or OpenMP, then you're limited to a single node. So at best, you can go 32 times faster. But if it's parallelized using MPI, theoretically, you could use all 16,000 cores. So, should you? That's the question. If you've got a simulation, you've got a full node, should you use all 32? If you've got the whole system, should you use all 16,000 cores? Well, there's no way of knowing this in advance without benchmarking your code. So these are two slides on how to benchmark, which I won't dwell on. But let's say we know how to benchmark, and we've got a particular code and a particular simulation. My example here is from a code called CHIME. It's an open source bioinformatics pipeline for performing microbiome analysis. It's actually Python scripts, and it's parallelized using threads. So we're limited to parallelism within a single node. So here's a test case I ran, and you can see as the number of cores increases, then the time decreases until you get to 32 cores, and then suddenly the time starts increasing again. So this is a very typical graph. People will use a log-log graph so that the lines appear straight if perfect. And as the core count increases, time reduces, levels out, and then starts increasing again. This is, as I mentioned before, the communication starts to dominate over the computation. So by looking at this, we would say 16 cores is the fastest execution time, so I will use 16 cores for my simulation. But is that really efficient? This slide just says what I've just said. So let's look at the parallel efficiency using the same data, so the execution times, but this time we've computed first the speed up and then the parallel efficiency based on the speed up. So we assume that on the one core you have a perfect parallel efficiency of 100%. And as you can see, the efficiency drops down and down and down, as you can see. So typically a target parallel efficiency is 70%. Some groups will use 50, others use 80, but we'll use 70 in this case. And you can see 70% gives us 8 cores as our target. 16 cores gave us the fastest execution, but that only gives us around 46% efficiency, which is poor. So to be more efficient, you should use 8. The efficiency when using all the cores in this node, that's 21%. So this slide just mentions what I've discussed. So the target core count for our example is 8, apparently. But yeah, 16 may be faster, but it's not efficient. So you don't want to waste your budget by using what might be the fastest. You want to aim for the most efficient core count. However, that said, typically HPC platforms charge you by the node, not by the number of cores you use. So that means in this particular case, we're going to be charged for all 32 cores in that single node. So now, the fastest result wins. Now 16 cores is the best choice. Actually, further testing will demonstrate that 24 cores is actually even faster, so that should be your target. Whilst it's not efficient, it's the fastest. And since you're paying for the whole node, 24 cores should be the target. Okay, so I have only 3 slides left. I just wanted to present briefly some jargon that you're going to hear in the world of HPC. First is high throughput computing, which is essentially task farms on HPC. So you'll have hundreds of jobs or thousands of jobs, and they're all independent, but they can be parallel themselves, and they are farmed out by a single master job to all the available processes. The other HPC jargon you may hear is high performance data analysis, or HPDA. This is essentially data analysis performed on very large shared memory nodes. I've mentioned network before. Other words for that are interconnect communications fabric, and this is the hardware used to send the messages between cores on different nodes. Then nodes, you'll also hear them referred to as servers, or shared memory systems, or sometimes they're called boxes. The processes, so each node has several processes in it. Sometimes these are referred to as sockets, and rather confusingly, these are also referred to as CPUs. And this is confusing because processes have multiple cores, and sometimes the multiple cores are also called CPUs. So it's a bit confusing. So personally, I would try to avoid the phrase CPUs. Very briefly, you may hear people talking about a memory hierarchy. This refers to the cache, which is very fast. Level 1 cache is fastest. Level 2 slower. Level 3 again. You'll hear people talking about NUMA regions, which is dependent on the cache levels and how tightly packed the memory is to particular cores within the node. And you'll find placing tasks within particular regions will affect performance. You'll also hear the phrase scripts, which are essential ASCII files, containing commands. And the example we talked about was batch scripts. There's the time budget, which is sometimes referred to as cycles or core hours, or indeed CPU hours. And then we talk about production runs, which are simulations that aren't tests, but are producing science. And then finally, as I've mentioned before, efficiency and scaling are you'll come across these words quite often. Finally, in summary, HPC is driven by the need for more and more computing power, and this is synonymous with parallel computing. Parallelism is available at many levels, from a data level to a task level, etc. And a good scaling means that a particular simulation on a particular application on a particular machine means it will run very efficiently as the number of cores increases. Access is usually via the command line, so you'll need to learn command line OS Linux and how to use an in-terminal editor. And then access to the compute resources is mediated via batch system. And finally, you'll need to benchmark a simulation which is typical of your target production runs to determine exactly how many cores you're going to use. And that's the end of this first half. And with that, I'll hand over to Gabor.
Thank you, Gavin. And hopefully you see my shared screen. Yes. All right. Thank you for the presentation so far, Gavin. I will try to introduce practically how these concepts that you've just heard work. And for that, I will use HemoCell, which is an HPC application, and I will run it on our local supercomputer. Afterwards, I will quickly explain what potential development environment can be used, what softwares you should obtain to be able to follow this. And then we will go on to execute an actual simulation. And finally, I will quickly show how to visualize the output. All right, so the application that we are going to use is called HemoCell. It can be downloaded from the website that's just shown on the left. It's a fully open source code. And you can see an example video of one of the simulations that we ran a couple of months ago. It's an artificial thrombus, red blood cells and platelets. And this type of simulation can be used to investigate transport physics of full blood, which can be useful in medical applications, for example, or development of medical devices. Now, this application, this HemoCell package, has already been deployed on a number of HPC machines. The one that we are going to use today is this one, a Surfsara operated machine, which is located in Amsterdam. Now, the question might arise, why do we need HPC machines for this particular code? On the screen, you can see 2 cubic millimeters of blood, which consists of approximately 8 million cells. Now, each red blood cell is described by around 4,000 equations. So if you think about that, you have 8 million of them, and this is just 2 cubic millimeters, so it's not even a drop of blood. You can imagine that for real applications, this can be a humongous computation. We chose 2 specific examples to execute today. One you can see on the left is a smaller one. It consists of a single red blood cell, and one on the right, which is a straight channel flow of multiple cells. The rationale behind it is to showcase how a typical development cycle of an HPC application works, because the case on the left can be executed even on your local machine, on your notebook. The computational cost is relatively low, so you can test how your computation work, you can check your simulation output, and when you are satisfied, you can, with the appropriate methods, scale it up to larger machines. So in this first case, we will reproduce a cell stretching experiment, which is we attach 2 silica beads to the 2 opposing ends of red blood cell. Then we trap those silica beads with an optical trap using laser beams. And focusing the laser, we can exert force on these silica beads. Technically, you can imagine it as taking one of these beads and starting to move it towards the right side. That will stretch, of course, our cell, and then we can record the deformation of the cell itself as a function of the stretching force. On the right side, afterwards, we validated our cell and we are content with its mechanical behavior. We can set up a simulation with more complicated geometries and much larger domains. Here we took a simple geometry of a straight channel flow and added approximately, I think it's 600 or 700 cells. And then we run it on an HPC machine. You can see on the lower right, that colorful video, that each particular small box is colored differently. Each of them represents a specific core. This was started up, I think, on 128 cores. And you can see as information exchange happens, because as a cell moves out from one of the domain, it has to communicate its location, various information to the neighboring domains. And this will show, of course, on the performance as well. We will talk a little bit about that later. Quickly about the suggested development environment. You will need one program for each of these categories on your local notebook installed to be able to compile and run HemoCell. These are very basic, typical development tools. First, of course, you will need a terminal to access the login node of the HPC machine. If you are using Linux or Mac, then you have this out of the box. Just open up a terminal and you can use the SSH command. If you are using a Windows machine or you would like some cross-platform solution, then PuTTY or Termius can be of help. For transferring files back and forth between your local machine and the remote login node, you can use the SCP protocol. Again, if you're sitting in front of a Linux box, then you can use it in the shell directly. If you are using Mac or Windows, then I suggest WinSCP or CyberDuck. These have added benefits that I will just display later. Then you will also need an editor. Of course, you can edit files on the login node as well, where you're most likely to have Linux, as Gavin pointed out, where usually you can find Nano, Vim, maybe Emacs sometimes. On your local node, I suggest you use Sublime Text, Notepad++, Text Wrangler, or something like that. For visualization, we will use PereView exclusively, though there are other visualization codes that possibly able to show the VTK output of these simulations, but there are particular properties of PereView that I will point out why it can be really useful for HPC application. For the file transfer, this is just a small side branch, because in my experience, this can really speed the beginning phases of development up. If you are using a graphical user interface tool, most of them have the capability to set a local editor. Now that means that you will have this two-panel interface, and on the left side you have your local machine, and on the right side you have files from the login node. And whenever you are editing something on your local machine, that typically means that you copy file from the login node to your login machine, edit it, save it, and copy back. Now these user interface tools can do it for you. So if you open a file for editing on the remote panel, in the background it will automatically download it, and whenever you save the file after editing it, it will automatically upload back to the login node. So it can take care of this procedure. Obviously there are other tools as well to do that. This might be the less painful because you get it out of the box. Quickly about how to get HemoCell. As I've mentioned before, you can download it from its website. If you navigate to Documents and Downloads, there you will find various options to download it. Now we will use the direct code repository download, which means that it will redirect you to GitHub, where you can find a download button that will create a compressed archive of the full source code. And you can just use the link of that download, or you can download it directly on your local computer and upload it using WinSCP, CyberDuck, or one of the SCP-based methods I mentioned before. After it, we will unzip it on the login node, run a really quick setup, and start to compile our first simulation case. Okay, so it's time for me to move to the terminal, and in case you happen to see some screens in between, that's perfectly normal. It just takes a few seconds for our webcast to change to the appropriate window. And now it should be there. So I quickly connect to the HPC machine with SSH, of course. And then I will quickly create a working directory and download the code. I don't want to spend time on this. This I'm sure you can do really easily. For downloading the code, I will use the tool called wget, which is available on most Linux boxes. And I've just inserted the URL link that I obtained from GitHub's website. All right, so now we are at the point that we have a working source code copied to our login node. And from this point, I can just show the contents of the directory quickly. And for convenience, we included a setup script that takes care of the basic setup of the code. Now, this is a very good practice to always check shell scripts before you execute them, just in case. This particular one downloads Pelabos, which is another open source code that takes care of the fluid dynamics part of the simulation. We download it from their site, uncompress it, and add a few modifications in form of patches. And then we will be ready to go ahead and compile the first simulation case. Now the setup just downloaded Pelabos. We patched it. And then to be able to compile our code, which is usually the case for every HPC package, you will need the appropriate compiler's dependencies. The way on HPC computers this is organized is called modules. You can see the list of currently loaded modules. These are basic default modules. On top of these, we will need a more recent compiler and several libraries, which are dependencies, and they are listed on the HimoCell documentation. The way to load them is to use this module system, but again, we have a convenience script that takes care of it. I'm just going to show it very quickly. What happens here is this part will take care of the module loading. You can see that it's practically a list of different packages starting from GCC. We are going to load them in. And let's see if it works. All right, so now you can see the difference in the packages. We already have loaded the appropriate ones. So now we just change to the simulation folder. We will choose this stretch cell first. That corresponds to the case that you saw on the left side on the slide. So this is the one where we stretch a single red blood cell. The folder contains the source code and the configuration files for this particular case. Again, we do have a convenience script for compilation, but you can do this by hand as well using the CMake build system. Now, this script suppresses most messages except for error messages. So whenever something goes south, you might want to do the steps by hand, by not suppressing all the outputs so that you can find out what the error was. Okay, so we have our code compiling, and in the meantime, let me jump back to the presentation for a moment, because this compilation might take up to a few minutes. This is quite typical for larger code bases, that the compilation itself can take up to minutes. And in this case, we will need two simulations. So the other one I compiled in the background ahead. The left one that we will start first is a smaller one, as I already explained, and it's important because typically this is where the development cycle starts. You create something that is possible to test even on your local computer. And then when you think that you got all the pieces in place, you can scale it up for a larger execution, which is going to be our second simulation. Now, just a little bit about this development cycle. First off, the code is usually set up using the login node. Now, these nodes, as Gavin already explained, are typically not used for production runs because it's But first, it's a single node. Second, many people uses it. So instead, if you want to try out something that is too large to run on your local notebook, there are designated queues for that on most HPC machines, usually called short or express queues. That means that you can submit your job the same as with a production run. However, there are additional constraints such as shorter wall time. You can request, for example, up to 10 minutes. After 10 minutes, wherever your simulation are, it's going to be canceled. This is designed so that people can quickly start up larger jobs and test out the code, how it behaves when you run it on multiple nodes, which is of course not possible to do locally. And afterwards, you can send in the full production run to a different queue, which is usually titled normal, for example. An alternative possibility is to request an interactive session, which will reserve a couple of machines from the computing backend for you. And you will receive an interactive terminal, such as with the login node, but you will have access to the computing nodes as well. Now, this is, again, part of the development cycle. You might find it useful for trying out your code. Afterwards, you submitted your run. You can use multiple command line tools to manage those runs, because obviously you can imagine that it's not only a single job that you can submit at a time. Let's say that you have a simulation that takes about a week to run. You don't have to wait for that week to pass and your simulation to complete in order to submit something else. When you have multiple of these jobs submitted, you can manage them, choose between them, or maybe cancel them if you figure out that one of them was started with the wrong parameter as such, with these command line tools. And afterwards, the execution, you usually turn to post-processing, for which you have separate possibilities. If it is a really lightweight post-processing, then you might just want to copy the data to your local computer and use whatever tools you have available there. But sometimes it's much more file operation heavy, because the post-processing have to mangle through several gigabytes of data, for example. Then you might want to do that on the login node using the HPC file services. Optionally, if it's computational heavy as well, you might as well submit it as a separate job. So by now, hopefully, our compilation is finished. So I can just go to our console again. This is the part where I mangle Windows. Yes, hopefully we are there. And if we just list the directory, you can see that we have an additional file called stretch cell, which is an executable. That's our compiled binary file. All right, let's check out the local running environment. You can use this lspci command to get detailed information about the local hardware, or for our purposes now, we are just interested in the number of cores. So this npros is a shortcut, which tells us that we have 16 cores available on this login node for testing. So let's start up our simulation on a single core first. I will allow the simulation to run for a few cycles. And then, meanwhile, you can see on the right side at the end of these long lines that it has a built-in performance measurement tool, which now approximates us that the performance is about 0.008 seconds per iteration. Now that is important for now, because we can check what happens if we start up the code using more cores. Let's put 8 cores to simulation, and let's see what happens then. We can already see that the computation is faster. However, if you check the performance, you can see that maybe with a linear speed up, we'd expect something in the range of 0.001 second. Now that is not true. We have 3.5 times higher execution time per iteration, which means that the speed up in this case is not actually 8, which would be ideal, but much less. And the parallel efficiency then is not 1, but less, approximately half, a bit more than half. So that is on the edge of being parallelly efficient, as Gavin explained those definitions. Okay, let's move on to the post-processing of this particular application. The output now is compiled into files that can be read by ParaView later, so that we'll be able to quickly view those. And then let's move over to the other simulation, the larger one. This one is called Pipeflow, and of course, I've already compiled it. So let's take a look at the job script. This is something similar to what Gavin has explained, because this system again has the PBS bash system. And in the first 4 lines, you can see comments which are actually parameters for this bash system, telling that we will use bash as a command line, and we request 5 minutes of wall times using 1 node and 14 cores per node. And in the last couple of lines, you can see the actual simulation command, which again uses that MPI run wrapper and requests 28 cores and 12 cores per node. Obviously, these 2 information do not match now, so there is an error in here. But let's just assume that we didn't notice, and we submit it as a work to our HPC system. For submission, we will use this QSub, as it was explained earlier. And you can see that we get back a job identifier as a message that it's been queued. Now, if we query the statistics, then we can get back that currently I have this 1 job submitted. The queue is the express queue, which is practically the short test queue of this HPC system. We do have the job name. The number of nodes is 1, of course, and the number of tasks, which is 14, and the requested time, 5 minutes. And the last parameter that we get back is the status, which is a capital Q, saying that currently our job is waiting in the queue and it will start at some point. Now, let's say that we realized we made some mistake in the job script file. So we can quickly delete this job using qdel. And of course, we have to give the ID of the job. It is deleted now. So if we get the list of jobs, we will get back an empty message. We can then quickly modify the job script so that it becomes meaningful. And I'm using MCEdit for the syntax highlighting, so you can distinguish more easily what's going on in this script. We will request 2 nodes this time, and also that means that we have to change the nodes per the cores per node parameter. Also, we will request a longer run, let's say 12 hours. That of course implies that it's no longer part of the express queue. So when we submit it as a job, you'll see, hopefully in a moment, that now it sits in a different queue called parallel, which is the normal production queue of the HPC system. Sometimes you have to specify manually which queue you want to target, but the basic principle is the same, that these queues can have different constraints. Sometimes they might even have different hardware. So whenever you specifically want to target nodes that employ GPUs or some accelerator card, you might want to use the specific queue for that. All right, we will not wait for it to finish, because who knows how much that might take. Instead, let me quickly switch back to our presentation. And finally, we'll go to the state where we actually evaluate the outputs. For that, we will use ParaView, and I will just leave this slide here if you need information later how to access this type of data with ParaView. We are using this software particularly because it is meant for large data sets. So right now, I'm going to use it on my local notebook, but it's also possible for much larger data sets like the one I showed before, the 8 million red blood cells, to set up multiple visualization backends. So you can turn PeerView itself into an HPC application where you actually attach rendering node backends, and then the computation for the visualization is done in an HPC system backend. So you can have much larger data sets than what your notebook actually supports. Let me change then to PeerView. And check out our red blood cell stretching. So here we have our red blood cell. We can visualize different properties. For now, I will just put the force on the membrane on it. And if I step to simulation, you can see subsequent time steps and of course how the cell itself is stretched out. In the meantime, we can add additional data sets to the same scene. For example, now I'm adding the surrounding fluid field. That can be useful in this case because we might want to take a look at the fluid velocity, how it changes around the cell. So now you can see that while we are stretching the cell itself, fluid moves outwards at the two opposing edges. And as it contracts in the perpendicular diameter, fluid moves in. So we create these 8 nice symmetrical vertices during the simulation. Let me quickly delete this data just to have a glimpse at the larger data set as well. Obviously, other data sets that are possible to add if your simulation incorporates multiple cells, for example, it's possible to add platelets, white blood cells, whatever you were computing. Here you can see the pipe flow simulation output. And now all the cells are colored by the computational node that took care of the computation. So every single colored domain is a separate core during this calculation. And finally, we can also add platelets here. And well, that completes our final view of the simulation. If you are actually doing some post-processing work, then at this point you can apply a multitude of filters to cut through the data set, to search for particular cells, to visualize forces or velocities on the membranes. So this is the way you can easily post-process a large data set if you have an HPC application. And with that, I think I concluded our talk. So both Gavin and I are open to questions, if there is any.
Okay, thank you, Gavin and Gabor. Are there any questions from the audience? You can type in your question or you can raise your hand if you have any. So someone is asking if you offer some support for Hemocell.
Well, currently we offer support through emails only, because this is of course an academic application and there is no corporate background for it now. But if your application is interesting, and I'm sure it would be, then we are always keen to discuss and help wherever we can.
Okay. So are there more questions? So if there aren't, oh, sorry, there's one more question. So what's the development landscape for Hemocell? Is it finished or ongoing?
I think that software is never really finished, so I wouldn't dare to say that. It's an ongoing development, and I would say that this is just gaining traction. So now there are a multitude of institutes who are starting to use it, and since it's a community that is starting up, that of course will lead to faster and faster development cycles. Right now, I'd say this is in development. However, the basis, the transport physics for platelets and red blood cells are thoroughly validated. Those are stable and fully functional. But of course, we can also add additional cell types, additional diseases like sickle cell or malaria infested cells, which translates to continuous development as well.
Okay. So we have one more question of John. What role do GPU, TPU, and QPU play in HPC?
Ooh, that is a sneaky question. I'm not sure if who is it asked from. So Gavin, do you want to answer that one?
I've never heard of the last two actually. GPUs are essentially a shared memory frame with thousands of tiny processors, each with a tiny amount of memory. And they're very good for particular calculations. Well, they come from computer graphics, where the rendering of each pixel to determine the color of each pixel is independent from every other calculation. So they're very good for these kind of regular meshes calculations. But they're not good for all calculations, of course. What were the other two? GPU and
tensor processing units and quantum processor units.
Oh, okay. So quantum processing units are certainly probably the future, although quite some time away. I've seen D-Wave presentations which are very promising, but I think in terms of applications, they're very nebulous. And tensor processing units, I'm not that familiar with. I can hazard a guess that they're probably something similar to vector processing units, where the CPU, rather than adding two numbers together, it can actually add two arrays together simultaneously in the same time it could take to another computer to add two single numbers together. Now I know there's a lot of vector processing units are actually such optimizations are widely available on a lot of HPC platforms. So a regular core, a normal core, that will have the compiler associated with that core will have a vector element to it. But you're asking about tensor processing units in particular, and really I don't know that much about them.
Mm-hmm.
Okay. So, thank you, Gavin. There's one more question from Maria. If you have any experience with mixing deep learning and HPC?
Well, from my side, I can plainly say that I do not have any personal experience with that one.
I've come across deep learning in a number of aspects, but all the cases I've looked at have not required HPC. It's all just run on a laptop. It's small enough to run on a laptop.
Exactly.
But there's no reason that deep learning could not be run on an HPC system. But be careful, the system has to be very large in order to be efficient.
Okay, thank you. So I think these were the questions. So I would like to thank Gavin and Gabor again for giving these presentations. This webinar will also be available on the webpage of CompBioMed. So if you want to look it back, that's of course possible. Also, the slides are available. So, and I would like to ask you if you want to help us to improve our webinars, you can fill in the questionnaire. It will pop up if we close the webinar. So thanks again. Thanks for attending, and thanks to the speakers. Bye-bye.
Bye-bye.